All right, as you can tell, there are two names on the slides, and there's only one person up here, unless you want to be Sergey Brodis for the afternoon. Yeah? All right. We can do this? All right, perfect. So if you may have guessed, my name is Jacob Torrey, and I'll be talking about going from theory to practice and back again with memes and GIFs along the way, and inducting you all into the cult of LangSec. So thank you all very much for coming. As theorists and academics, we get to be snide and kind of condescending from our ivory tower. So exploits will be patched, but LangSec is forever. Real quick, who are we, or who am I? I live in Denver, Colorado. I like cat pictures, and I usually do low-level security research, so hypervisor, EFI, BIOS-type security. Sergey is a professor at Dartmouth College, and we're both co-conspirators in this cult of LangSec. We have an outline. So, problem. So, because there's a lack of objective and comprehensive metrics in security and software development practices, ad hoc or cult-like development practices have occurred. So there's development based on tradition, like this is how the person when I started at a company told me how to do it, or this is how my professor told me how to do it. And there's very little way for us to kind of question that and figure out objectively, is this way better than another way that someone else has told us? And you can kind of get into these little cult wars if someone says VI is better than Emacs. I think you guys all know that objectively Emacs is better, but the VI people are just kind of slow to get that, right? And so that's what we need, is we need metrics to be able to understand that. I think some of the current issues of today have highlighted, especially as of yesterday when basically the US decided it didn't want to do Twitter or GitHub or the news. Basically the status quo is not doing too great. More software is being written than ever before by a more diverse group, and secure composition of all of these components and libraries is very hard. So I'm sure in the future, we have pwned by a cloud-enabled light bulb. Now it's a cloud-enabled computer video camera. So that's kind of where we're at right now. So a keynote last year at Troopers by Sergey talks about the theoretical underpinnings of cyber insecurity. It's a great talk. It's on YouTube. Check it out. It's called My Favorite Things. The field of LangSec basically uses computational complexity theory to argue about the root causes of vulnerabilities and why exploits exist. So exploits are basically these weird machines where data is the code that the program is the interpreter for. So exploits are proofs of insecurity, and they are just basically deciding how the program should run outside of the intention of the developer. So we also need a software development lifecycle, SDLC, in order to take LangSec and put it into practice. And that's what we're going to try to talk about today. So hopefully after this talk, people will understand what LangSec is, how it has a crucial impact to building secure software, have a framework to transition that into practice and into their development practice. For those of you in the room who are developers or write software, raise your hand. All right, like 3 people, great. So for those of you, you'll be able to recognize dangerous constructs and avoid some of these defect-prone semantics. And I'm assuming that everyone else is a program manager, right? Everyone else is a manager, no technical skills, perfect. You're gonna get to audit these 5 people up front who are developers. And so you can then use this to sell the underpinnings and the theory to increase your corporate buy-in and get a bigger budget to go travel to conferences around the world. So all in all, this should be a great talk for everyone. So I think, as we've seen for the last 15 years, bugs will happen. How you structure your SDLC basically dictates where in the process that finding process will happen, right? The sooner you find the bugs, the happier you are, because the cost goes down and the impact to your bottom line. We've also seen, I think I have 10% battery life. Someone who's staff or, excuse me, staff? I have 10% battery life, so I can go really quick. I have another like 70 slides. Yeah, right there. Fantastic. So a lot of organizations have kind of arrived at these theoretical underpinnings kind of by happenstance, and so we want to make sure they don't just happen to move away from them somewhere else. So talking about finding bugs, right? See how happy all these people are? They found a bug during a meeting, and they're also in a stock photo, so that's why they're being paid to be happy, right? But they all found this bug at the design and architecture review. So they haven't even written a single line of code, and they've already fixed a bug, right? This guy, I mean, look at him. He is thrilled because his compiler told him he made a mistake, and he was able to fix it now rather than having to get a bug report and a QA guy calling him at 2 in the morning because production is down. And at Google, they're losing $1 million a minute because their ad system is down. I think that's, I have a friend that worked at Google, and he said, you're not a real Googler until you've cost the company at least $1 million. So this guy's happy because he's not a Googler, right? This guy's in dynamic testing and QA, quality assurance, and he's hoping that the QA guys are good and that his dynamic testing is going to get to some of those code paths that are a little sketchy, but he's not so bad. This is not as good, right? When Liam Nilsson calls you and says, I have a bug and I'm going to find it and basically pwn you, that's not your ideal situation. And certainly, bug bounties are good in that sense that now they're going to at least tell you, but you still need to get that early phone call and have to deal with it, figure it out, and scramble resources. And then there's the last case. So this is, I don't know for you guys who don't know, recently in the US, the OPM, which is basically handles everyone's clearances, they got massively owned. And this was the director getting hauled in front of Congress trying to explain why, even after the Attorney General told her to shut everything down because it was insecure, she ignored the Attorney General and just kept doing it. So she's not the happiest person in the room right now. You also don't want to be hauled in front of the US Congress, probably. All right, so now that we have kind of the overall frame of how we want to do this, let's take a very concrete example. So DNP3 is a protocol used a lot of in like industrial systems and power control systems. And so my co-presenter right here worked with a few other folks. He had an academic, he had an industry guy, and then kind of like a government folk to be able to see what we could look at if we designed a DNP3 parser from the ground up with the LangSec processes. So what is LangSec? So LangSec posits that security issues stem from a lack of recognition of the language. And so an exploit is basically allowing bad input to come in and take over that process. And so the question is what do you accept, what is expected, and what is valid? So a great example of this is return-oriented programming. Basically, you're allowing the attacker to give you an assembly language of return addresses that then is reorganizing the execution flow through your binary. And so technically, you've allowed them to do that because you've created a weird machine or almost like an ad hoc virtual machine that is now running that return-oriented programming exploit. So we see a lot of this stuff, a lot of fails. And then if you look at some of the things like Heartbleed, which we'll talk about a little bit later, if you look at the complexities of some of this code that's getting owned, there's basically, it's getting way out of whack in terms of how complex it needs to be, and we'll see with DNP3 some really concrete examples of that. Some of which we're going to call poison. So anytime you have a nested length field, fields that have to agree that might have happened out of order, etc., you get into some weird situations where you're trying to figure out if this input is valid or you should reject it because it's possibly some form of exploit. Fun fact, so the PDF spec, you can actually have the length of an object point to another length, and then that one can point back. So you can basically make a circle, and you can make the Adobe Reader go in a circle for a long, 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 long time. So that's kind of an example of maybe some syntactical poison. So a couple cool quotes, right? Data format is code's destiny. And then the other one is basically the complex specifications that managers are creating and then forcing software developers to use are complicated enough that they should be verified using formal methods or some other form of automated techniques. But basically, because they're so complicated, the algorithms needed to verify them are undecidable, which means they'll either say, yes, this software has a bug in it, or I don't know, and it'll take until the heat death of the universe for me to tell you. So that's what we're trying to address. So here we go. We're going to start with a grammar. So this is basically what we want DNP to be able to communicate and the format for that. If we don't know what that is to start with, how on earth are we going to expect that anyone can write software for a protocol we don't even know. Yeah, so then also if the protocol comes without a grammar, you're in big trouble. And then once you have that grammar, then you can basically start from the very bottom of these kind of little pieces of it and build it up in kind of a very iterative way that you can test in each increment. That way you don't have to have the whole testing everything when it's done. You can test each part. So what do we do to do that? Parser combinators. So basically, we can start with a really small unit of data, and then we can build them up to make bigger units. Imagine like a structure, and I'll talk a little bit later about a way you can do this. So you can handle very complex data structures, and I'll talk a little bit about Hammer. So Meredith Patterson was supposed to come and present, but she couldn't at the last minute. She was going to present her work, which is actually Hammer, and I'll have a couple slides in there. So for those of you who are really interested, I can at least tell you what it is, and then you can reach out to her. So back to DNP3. It does have issues. If you want to count CVEs, there are some of them. They tested about dozens of implementation, and very, very few had no problems. They also had set up a special fuzzer for these implementations, and they were able to find more crashes. Those that had the fewest defects basically chose a subset of DNP3. So what happens when you have a bad specification? So OpenSSL, if you looked at their parsing, it's, as Sergey says, pointer salad. Basically, you're trying to figure out what it was doing, and you have no idea. And so in the next slide, I'll show you the Heartbleed bug, and then the fix for it. And then basically, for those of you 3 developers or 5 developers, raise your hand when you understand what the underlying issue was, and then when you can come up on stage and describe it to everyone, all right? Another issue is for ASN1 parsers, which are used in a whole bunch of encryption. So ready? Developers, go. So it's something in that 1 plus 2 plus payload plus 16 is greater than S to S3 to RRX. So clearly that's defined in some RFC 6520 section 4. So, I mean, well, that's pretty obvious. So these are what we call shotgun parsers. Basically, it's like someone took a gun loaded with a bullet or I guess a shell with parsers, and they strewed it all over their code. So it's like spaghetti, but it's not as tasty, and it's full of lead and will kill you. So another thing, complexity does not grow uniformly. They have something known as the Chomsky hierarchy, which describes how different languages get more and more complicated, and they can handle more and more powerful inputs. Like regular expression is a lot less powerful than like a Python interpreter. Fortunately, once you hit a certain level on that Turing completeness, you've fallen off the verification cliff, and you can no longer make kind of very complicated reasonings about software in any kind of useful amount of time. So basically, you've hit this cliff, and now you've fallen off, and now you're very sad. Let's take a look at DNP3. So it has multiple layers, just like all of our favorite protocols. Is it complex? So you have some fragments in there and some objects. So far, we're looking pretty good. This seems like most everything we've seen. And then wait a second, what is going on here? And now it's getting very complicated. And that's just even parsing the syntax. Now let's look in the semantics. I don't know if you can read this, but basically there's like a time thing that you can add another object after that says, oh, that previous object that I wanted to read into is actually a write. So now it'll change your behavior of that in the past. So that's not so great. Another one is the date. You can have a time object, or I guess a time of occurrence, which is usually the absolute time. But then later on, you could get an object that says, oh, by the way, that object you received previously, that was a relative time to another object, which you may already have or may not, but you might have to look back and find it. So basically, you're just kind of constantly trying to figure out something, and it's a really kind of awful situation. So when we tried to develop this DNP3, we wanted to try to make the control flow graph as close to as possible as what the specification says. We wanted to obviously avoid duplication and abstract, and we wanted the code for parsing the data only in the parser, none of that shotgunning. So also, when we did this, we could capture the true syntax of DNP3, because if you read the specification, there's a lot of very vague words. This way, we can actually understand, and by going through this process, it can actually force us as developers to understand what the specification should say or does say, and be able to ask those questions before we're hauled in front of Congress. So parser combinators, this is an example using Hammer. So basically you can get sequence number and a bit. So you have some number of bits set out there. You have choices or many plus, or at least one or more. And you can define your own combinations thereof. So here if you have a fragment header with all the flags in it, you can pretty easily kind of build them up with some sequences higher and higher and then combine them all together. Another example is this CROB object, and you can see the kind of code related to that. Oh. More of that. So one of the interesting things, actually the only kind of crash in our parser was when you had a stream that had no objects. And we got to the point where we were trying to think, should this be many or many plus one or whatever? And we kind of made that assumption, but we had to actually ask that question. And so we were able to kind of come up with that and figure that out during development time. So we were like that kid going, yay, rather than the sadder person. So anyway, so this all was really great in the sense that we were able to have this discipline roadmap to develop it. We wanted to continue testing it just like we usually do, but it's a lot easier to test as well because we can test each kind of individual chunk and then build them all up on top of that. So then what did we do? Then we had basically two devices that were communicating over DNP3, and we were able to kind of break them out and parse them. And then we would fuzz them in basically observe-only mode and kind of see what would happen. And then we were also using AFL, which you guys, if you are trying to fuzz stuff and you don't know what AFL is, you should grab it. It's really nice. So basically, we were able to fuzz both with a model-based fuzzer for DNP3, as well as more of a generic kind of coverage-guided fuzzer. So our parser only had that one bug for the most part, at least as far as we can tell. We were able to get really high test coverage. And by doing it from the specification first, rather than this ad hoc parser where we kind of think about what we think the attacker is going to do, and that's the only state we can encapsulate, we're able to do it in a much more kind of focused way that helps us ask these questions as we go along. So DNP3 was well-intentioned and it wanted to be simple, but then it got really complicated when you had like objects in the future that can change the objects in the past. So that's a problem, but it could be there. So verification, basically, as I said before, developers are not infallible, not perfect, and we really shouldn't expect them to be. So there's I think originally a Russian saying, trust but verify. So you can use static analysis to look for the bugs, which we just had a whole talk about using static analysis to look for malware samples. But unfortunately, certain runtime semantics are lost. Like if you have kind of dynamic function pointers or whatever, those usually kind of get lost. Dynamic analysis runs the program as it's looking through it, but you have a challenge of coverage, and also it takes a lot longer. So we had an interesting challenge in the program verification automatic exploit generation area. So there was a bug that Mark Dowd found, I think in like 2003, 2005 in SendMail. Basically it was called the crack adder bug. It was a while loop that was expanding email addresses and then making sure that it was matched in terms of braces and parentheses. And the semantics were very abstracted. It's still saying my battery is now down to 7. Okay. Basically, what they found out is that I'll just go fast. It only went down 3%, and I only have half more slides, so I think I should be good. So dynamic analysis then requires an NP-complete problem to be solved. So unfortunately, as the software code base grows, it becomes very challenging. So Crackader, basically, it was proposed as a hard problem for verification. Could you either develop software that could find this bug and automatically exploit it, or find this bug and automatically tell a developer to fix it? It was very, very challenging, and only recently has someone been able to actually find it, but they kind of had to know what they were looking for. And it's very, very hard in practice and in general just give it all of SendMail and say, find that bug. We kind of already talked about parsing, basically, where you want to make sure that there's a boundary between the program input and then when it's actually finished parsing, then you can start executing on it. And that comes from all sorts of things, reading user input, RPC, et cetera, et cetera. You want to start with the specification, and then if it's not compliant, you want to actually reject it. Like, see how happy she is that she was rejected because it was an invalid parser? Like, she's trying to kiss the cat, and no, right? Why do you want to do this? Because there's a lot of issues with parsers as they get more and more complicated. So there's a term called parser differential, where basically once your parsers get really complicated, it's almost impossible to figure out if the two parsers that should parse things the same are doing that or not. So one example is Bitcoin was using the ASN1 spec, and actually you could generate a specific transaction that 32-bit systems would agree and say, yes, that's a valid transaction, and 64-bit systems would not. And you could actually fork the Bitcoin pool after this. And so they had to fix it and then wait over a year before they were allowed to release it, because otherwise they could basically break the blockchain. Another really good one is SSL certificate parsing on Firefox. When you go and you register and you get an SSL certificate for a website, the certificate uses Pascal strings, which has the length of the string and then the string. And so I could go and register paypal.com null terminator attackersite.com, and as long as that was correct, there would be no problems in the sense that I was actually asking for a certificate for a subdomain of attacker.com. And most browsers would detect that that was not valid for actually paypal.com. So if you're trying to man in the middle someone, that wouldn't work. However, in Mozilla Firefox, they would assume that that certificate was using C strings. And so it would read the name of the site, and it would stop at that null terminator, and then it would say, yes, this is a valid certificate that chains all the way back up to VeriSign or some other root or authority. For paypal.com, you can enter your login and data password. So again, we're sitting in our house, and it's on fire, and it's all great. So there's a lot of conventions out there trying to make software more safe. So MISRA-C is like industry and safety for cars, and they know that there's a lot of safety critical stuff in cars, and so they actually have built a whole bunch of tools and code examples for how you should validate your code bases to make them safe. And if you want to go even further, you can go to space, right? Hey, something happened. Yeah. Okay. Who'd have thought, plugging it in, huh? So NASA's Jet Propulsion Laboratory, they have to write code that runs in space. And it's very, very challenging to really go up there and push the restart button once it's crashed. I actually have a friend that had to disclose a vulnerability on the Mars rover, and that was quite the coordinated disclosure, because you're talking like 40-minute round trip time for radio signals to go back and forth. So they really want to make sure their code is as safe as possible before they ship it out thousands of miles away. And so they developed basically a top 10 list for safety critical code. And their goals were, reduce the defects, make verification easier, because again, they trust their developers are good, but they're not 100% infallible. And really, when we looked at these, it just kind of happened that they mapped very nicely to LangSec principles. So the stuff that was developed to run in very weird environments in space mapped very nicely. And so we're going to talk about some of those. So some of the top 10. So reduce the control flow complexity as much as possible. Don't use go-tos. Like, remember, maybe Apple had the go-to fail bug. Long jumps and recursion, because that makes your control flow graph into cycles, which is much harder to verify. If you get rid of recursion, you might have an acyclic graph which you can analyze. And then also, it makes your programmers think a little bit harder about what they're trying to get done, and that might mean that they put more intent into the software specifically. Rule number 2, all loops should have upper bounds and iterations. Basically, you want the analyzer to be able to determine termination. Obviously, some loops are non-terminating. It would be really silly if they made a scheduling loop for the Mars rover that only had 1,000 iterations before it just quit. That would be kind of a waste. So those loops, though, you should prove why they need to be non-terminating. Another good one, rule 3, basically do all of your memory allocation and memory changes before your business logic. That way you can analyze the memory map much easier, and also you can guarantee that your business logic is not going to start until all of your allocations have succeeded, and you're not getting into a weird situation where you've kind of already allocated half of some structure, and then you realize you have no more memory, and now what do? Do you start deallocating, and you've already sent an acknowledgement package, so they're going to start sending the next one, so what do? Also, it's really nice if you can use LD preload or Valgrind and basically create malloc that fails randomly to see how your program can handle it. Again, for those 95% of you that are managers, if you're looking for a devious trick, that might be something fun to put in your continuous integration suite. Rule 7, so this is a really interesting one. You want to check all the parameters in each function. Much like the network has been designed where you have a nice soft GUI interior and then a soft GUI exterior, a very hard and defended exterior. You want to make sure that a parser bug doesn't propagate through where you have some function that's your input, and then after that it's just deemed trusted. Because what's going to happen is down the road you're going to leave your company, someone else is going to start, and they're like, oh, you already wrote a function for this, great. I'm just going to put it out as a web API, and everything's going to be perfect. And so that's kind of a challenge, and one way you can do that is by fuzz testing and doing unit tests with fuzzers in your QA step, and that way that you can make sure that your internal fuzzers or your internal functions are a little bit more resistant. Another one is listing your use of pointers. You don't want that pointer sal like we talked about earlier. So they basically shift problems from compile time to runtime, which makes static analysis less powerful and then forces you to do more dynamic analysis. And I already talked about the PDF specification where you can have recursive pointers. So not so good either. So to really hammer the gavel on this, strict parsing. Input data, you should scrutinize it as much as a compiler looks at the code when it's trying to compile your code. And as those of you who are the programmers up here, you know that if you forget a semicolon, the compiler doesn't be like, that's okay, you probably meant to put a semicolon there. And I'll talk about a more specific example a little bit later. Invalid input must be rejected, and never rewrite that input trying to guess what their intent is, because that means the attacker can try to trick you into thinking what their intent is. So that guy right there is the guy who made Amazon. And basically, he had this mandate. And I don't think you can probably read it unless you're in the front row. Oh, geez. OK. He made this mandate. So apparently, he's known for micromanaging. And he just sent this email out to everyone basically saying, all your data and functionality must be a service. Teams must communicate only through these interfaces. No direct linking, reading of other teams' data store. Everything has to be a service. It doesn't matter if you're using HTTP, Cobra, whatever these things, doesn't matter. And then basically, all of these services should be designed to be public facing. Anyone who doesn't do this will be fired. Thank you and have a nice day. And then I guess the Amazon employee who posted this said, ha ha, those of you who worked at Amazon, folks, would of course realize that number 7 was a joke because Bezos most definitely does not give a shit about your day. But there's actually very interesting things here because by doing this, he was able to get Amazon to the point where it can become a services company, and now you see how powerful their web services platform is because he got all of his developers basically on threat of being fired to focus on making everything a public service, and they had to think about their data format and basically put it out there for other people to attack. That's what I like to call a verification-oriented paradigm. You heard of functional programming, you've heard of object-oriented paradigm, now you have another one. It's basically a meta-development paradigm. How can you make your developers, or if you are a developer, how can you expose as much of intent about what you're trying to do to the compiler and verification tools so they can help you do your job? So a quick example, if you're looping, aim for the induction variable, basically the variables that change, to be really easily identifiable. Then the compiler can do a loop unrolling because you can actually figure that out and you can make your code faster. You don't want to overload types because, again, that means there's more ambiguity about certain things. So there's some certain benefits. We kind of got all this stuff. Here's a graph from some software engineering book. Basically, if you are fixing a bug really early on, it's really cheap. If you're fixing a bug in production or operation, it's really expensive. You want to be doing it sooner because it's a better business thing. So all of you program managers, here's a good example. So for those of you programmers who maybe want an example, like a little bit more concrete, this is a really simple development trick that allows you to push what could be a runtime bug into compile time. So this is C code, not really, but basically, if you have a variable and you're checking against a constant, the first one and the second one are slightly different but semantically equivalent, right? You're either checking if the variable a is equal to 10, or if you're checking if 10 is equal to a. No big problem. So as long as you implement them correctly, you're all good. If you fat finger and forget about that second equal sign, the first one will compile, and now basically you're doing if a is assigned to 10, and that means it's going to be a runtime error or some semantic ambiguity. The second one will fail to compile, which means you're like, oh shit, I forgot that extra equal sign, no problem. So that's a really small example. I think actually from the keynote today, another one is just if you do if and then a variable, you're basically assigning anything that's not 0 to be okay. And as we saw before, that means someone that can corrupt even encrypted data can then set it to not 0. So reducing complexity. We try to implement the least privilege principle in the network. You don't give everyone root. If any one of you guys connect to IRC and your username is root at, whatever, means you're logged in as root, you'll get laughed out of pretty much any security channel. So don't do that. But I like to argue that computational power in and of itself is another form of privilege, and we're pretty much running everything as root. So AV usually relies on having more privilege, thank you, than malware, and it doesn't work if we're all running in the same level of computational power. So here's an eye chart that shows you that. Basically, there's the Chomsky hierarchy on the bottom, and then your more traditional privilege of user and admin, and then ring 0 and the kernel and hypervisors. And you look at a whole bunch of different data points, and almost everything is running in the more powerful side. More complex problems lead to more complex bugs, more chances of error, less chance of detection, and then getting hauled in front of Congress. So the rule 2, limit looping, will restrict your growth, and it improves verification. So I have an IEEE paper where I wrote a compiler that is provably sub-Turing, so you can't write a non-terminating program in it. And we found that A, very few computations actually need that, or if you design your application properly, say you have a PDF reader, the actual parsing of a PDF file should never take an indeterminately long amount of time. It should be some polynomial function over the size of the file. And then your UI loop, that can go forever because you have no idea if the user's walked away to get a coffee or is dead, right? So very few computations need that, and if you isolate things out, and then we also showed like pretty good verification and security benefits from that. And that was also done manually on the SDL4, which is I think the only formally verified microkernel in existence out there. It's open source, it's pretty cool, but they did that by segregating bounded and unbounded code manually and then doing a lot of verification work. So tools for enforcement, it's really nice to know all this stuff, but if you're like me and you're lazy, you're not going to do them unless someone is telling you or beating you with the stick, right? You know, morale will improve, or the beatings will continue until morale improves, right? So how do you do this? How do you encode this into your development process? SDLC, so code reviews, function testing, QA, et cetera, et cetera. Obviously, you want to scale for effort, right? It's just like technical debt. You want to figure out where you're comfortable and where your organization should sit. You know, you want to spend the most amount of time in figuring out where you're going to be in your specification, because again, data's format is code's destiny, so if you can figure that out, you're going to save yourself a big headache down the road, and then doing a little bit of dynamic analysis, fuzzing, unit tests, and then you don't want to get on the front page. There's some tools out there, cool. Crem I talked about, it's open source. If you're curious, it's basically, it's embeddable domain-specific language that you can use for parsing. It's got a familiar syntax. You can use formal parser generators, but Hammer and Nom are ones that Meredith was going to talk about. They're designed for complex data parsing. And so basically you can plan your specification and you can implement that. One example of a fail in that is the IP version 6 fragmentation. You can actually scramble the packets up so long that it takes a WAF or some kind of firewall so long to recompile it that it just has to pass the packet through in order to deal with the quality of service guidelines, and then it can pass things through. So there was a talk by some ERNW guys a couple years ago where they would just send a simple SQL injection that should have been caught by the WAF, and they just reordered the packets, and then the thing went right through. Nail is something built on top of Hammer that basically allows you to write a data structure, and then it will automatically generate parsers and generators for that while rejecting anything invalid. So here we have a really simple example. I'm going very quickly because we're on the clock. Basically, you have an employee database which has an employee name and et cetera. You basically create this little structure right here of a person, then a database is basically comma-separated many people. And that will automatically generate a parse person and a parse database, and then a generate person, a generate database, and all the structures you need. And looking at this code makes a lot more sense than looking at something like that OpenSSL code. Another cool tool is CLE, which is a symbolic execution engine. You can gain really high coverage of code, and you can find crash cases or verify semantic differences in between certain areas, like checking for parser differentials. So what is symbolic execution? Basically, when you're running your software, whenever you reach a branch, you execute both paths of them, and you maintain the constraints on how you would have gotten there. So you start off with x equals x, and you go down there, and then basically there's a conditional statement, and you just assume, okay, the constraints on the program is that x is less than y for the left, and x is greater than or equal to y for that, and say if that false case crashes, you can then solve the constraints on that and get a real input that will crash your program. So there's a quick tool I'm going to show you about that, and then I'll get out of here, and I think it's break time. So the Pope came to the US, and it's pretty cool. He performed a miracle. I'm not sure if you guys heard about this. It's really neat, and I just threw this in there because I thought it was a funny GIF. Wow, ooh. All right, so I made a quick open source little toolkit that I'm building right now to do some of this. So you could add this if you're a masochistic or sadistic program manager. You could add this into your continuous integration stuff. Basically, there's some memory management failures. You can cause random failures of your memory allocation. You could have a header file that can poison certain bad things like getS or some of those ones that are known to cause problems. And then the one I'm going to talk mostly about is automatic symbolic testing for parameter verification in every function. So basically automatic unit test generation using symbolic execution. This one pretty easy, that one's pretty easy. All right, so CLE unit is the name for that. Little 90s, I know. So CLE, when you give it a whole program, rarely will it find every single bug, and it requires a lot of computation. We did this on some programs, and you end up running into an NP complete problem for solving those constraints, and those take longer and longer and longer, like on the order of hours and hours and hours to solve a whole program. And that can find really interesting bugs where if you have some state of the program over here that interacts in a weird way with the program over here, and that's something that's going to only be found through like functional testing or really kind of guided fuzzing. What I was thinking about doing is I hate writing unit tests, and they're so silly for a small function. Is there a way that I could speed that up? And so basically what I wrote is a C parser that for each function in your program, it generates symbolic values that are passed to that function that execute every branch in that little function. So you're not going to find insecure composition. You're going to find just little kind of flaws. I have a demo of it I can show you guys later offline because I'm running low on time. But basically, I wrote a program that has a slight divide by zero error in some cases, and I'm able to automatically find it and point out to where I need to fix it without having to write a single unit test. So that's something cool. It's available on GitHub, and it still needs some work, but kind of nice. So in conclusion, as we're down to our few minutes. All right, yeah. These slides will all be posted online. I don't know why everyone takes pictures of slides, but they all come out crap. I don't know. I was at Syscan, and there was like 15 Chinese people with big SLR cameras taking a picture of every slide, and I told them the slides were going to be posted online, whatever. Anyway, so the perimeter grows weaker. Network defenses must shift to more hardened applications. So Alex Stamos has a great talk. It's on YouTube called AppSec is Eating Security. One of the most pivotal lines in it is the time that a firewall has to make a determination about whether or not a packet is malicious or not and whether to drop it or not is the same amount of time as a photon does when it bounces off my toenail and into my eye. And as we move towards 40 and 100 gigabit systems, that's going to get even shorter. So I'm on the average height, but now imagine a much smaller person. That gets incrementally more difficult. And so we have to harden our applications. So my prediction, Nostradamus Jacob, says LangSec is eating AppSec. I think Google's Beyond Corp initiative showed that the perimeter leads to that false sense of security thinking that, oh, it's okay to do something really silly because I'm inside my network. And that is an issue that also comes up with application security. A quote I made up, to err is human, to be caught at compile time, divine. Secondly, when you're trying to do your tooling in your organization, trying to add some of this stuff into your SDLC will hopefully improve the semantic quality of your applications, and the verification of that allow you to trust but verify. And also, for those of you program managers out there, it's not just for security. It's less expensive because now you're spending less time in QA and less time dealing with bug reports. because you're reducing bugs in the long term. And then also you can sometimes get some faster code because the semantics are more easily understandable by compilers. And currently, I would say the state of software quality highlights the need for us to adjust strategy. So with that, I'll open up for some questions. Wow, okay. That's my joke about Python. You write some code in Python and everything's great, and then like 3 days later it crashes. Okay. If you want to take some more pictures, I have more links. If you want to take a picture of that YouTube link and then type in manually that hash. I have some more too that are even longer. All right, well, if there's no more questions, I think it's break time. And thank you all very much. And enjoy your coffee and free alcohol.